Hello. It is raining and thundering and lightninging pretty heavily outside right now. So if you hear any low rumbling in the background, that's what that is. But we're going to go over the summer 2019 final exam, questions 1 through 8, which are all of the questions that are relevant to midterm 1 for summer 2020 and theoretically onwards if they're using the same syllabus. This is everything up to 6.4 from the current textbook. Okay, question 1. Which of the following is an eigenvalue of this matrix right here? Well, remember, for finding eigenvalues, we're solving the determinant of a minus lambda I equals 0. So that's the determinant of 4 minus lambda, 0, 1, negative 2, 1 minus lambda, 0, negative 2, 0, 1 minus lambda. And if you think back to whatever linear algebra class you took, you know that we can rewrite this as 1 minus lambda, because it's in a column by itself, 1 minus lambda times the determinant of the matrix that we get by crossing out 1 minus lambda's row and column. So that's 1 minus lambda times the determinant of 4 minus lambda, 1, negative 2, 1 minus lambda. That gives us 1 minus lambda times 4 minus lambda times 1 minus lambda plus 2, and all of that's equal to 0. Now inside here we will get lambda squared minus 5 lambda plus 6. Lambda squared minus 5 lambda plus 6, which can factor, what will that factor to? Lambda minus 2, lambda minus 3. So lambda minus 2, lambda minus 3 in there. Okay, so here are our eigenvalues. We have lambda equals 1, 2, and 3. So C is the only answer that actually has that eigenvalue. Well, you know what I mean. 2. There we go. Question 2. If the differential equation given here is converted into a linear system of first-order differential equations by setting x1 equal to y and x2 equal to y prime, then what is the matrix P? So if we expand this system out a little bit, it will look like x1 prime x2 prime is equal to a, b, c, d times x1, x2. And if we were to rewrite this even further, this is the same thing as x1 prime is equal to ax1 plus bx2, and x2 prime is equal to cx1 plus dx2, little d. There we go. Okay, so we're going to need to do some substitutions here to figure things out. So we know that x1 is equal to y, and we're told that x2 is equal to y prime. Well, since we need x1 prime, we're going to need to take the derivative of both things in this equation. So we see that x1 prime is just equal to y prime. And what is y prime in terms of x1 and x2? Well, y prime is just x2. So I'll replace that with x2. Now, for our, for our x2 prime here, we'll need to take the derivative of both of these guys. So we see that x2 prime is equal to y double prime. And what's y double prime equal to? Well, we can use this equation here. Y double prime is equal to negative 2 y prime minus 3y. And since we know that y prime is equal to x2 and y is equal to x1, we can do that little replacement operation right there, stick these equations together, and then rearrange it a little bit so it's in the correct order. And we have our solution right here, even though it probably doesn't look like that. Because we know that the a term here will be the thing multiplied by x1 in this equation, so a is 0. Our b term is whatever constants multiplied by x2, that's 1. Our c term is the thing on x1 down here, so that's negative 3, and negative 2. So we're looking for 0, 1, negative 3, negative 2. That gives us A for question 2. Question 3, this matrix has a characteristic equation given there. Find alpha such that the matrix has 2 real eigenvalues with opposite signs. So we're just going to run this thing through the quadratic formula. Negative b over 2 is 5 over 4 plus or minus the square root of b squared, that's 25 over 4, minus 4 times A times C, 25 over 16 minus 3/4 alpha. Okay, let's factor, well actually, no, let's not do that yet. Let's just multiply this 4 in, we get 25 over 4 plus 3 alpha, which just simplifies down to 3 alpha right there. So we're looking for two real eigenvalues. So what do we know for sure? We know that alpha has to be greater than 0. If alpha is less than 0, then we'll get the square root of a negative number, and that will give us a complex eigenvalue. So alpha can definitely not be less than 0, and it also can't be less than anything that is greater than 0, because this guy right here includes negative alphas. So that's also no good. What about really, really big alphas? Are we okay with that? Well, if alpha is 10,000 or something, we're going to have 5 over 4 plus or minus some very big number. That will give us a positive real eigenvalue and a negative real eigenvalue. So there's no reason why we should be capping the upper value, the upper level, you know what I mean, the upper ceiling of alpha. So we should allow really high alphas in here. But what about really, really small alphas? What if we plug in alpha equals 0.0001? Well, as alpha approaches 0, our eigenvalues are going to both approach 5 over 4 from opposite directions. So obviously we can't have really small alphas. So this guy is no good because it would include alphas like 0.001. What about C? Well, yeah, C is correct, but let's see why. And you could have just solved for this manually. You know, using some inequalities or whatever. I personally, I'm really bad with inequalities, and I don't trust them. So I like to use the answer choices to my advantage. So let's plug in alpha equals 25 over 12. That will give us 5 over, well, I have it right here. So 25 over 12. This becomes 25 over 4, right? Yeah, okay. So then this becomes 5 over 2, which is 5 over 4. And if alpha is any bigger than that, then this guy will be slightly bigger than 5 over 4. And when it is, we're going to get, a positive eigenvalue and a negative eigenvalue if these are both our lambdas. Okay, I don't really like that explanation that I just give. I hope that makes sense. And I hope you see how you can, with these kind of questions, you can often just use the answer choices to figure out which one's correct. But if that doesn't work for you, please just go through and solve for it manually. It's not too bad. Question number 4. The phase portrait of a certain system is shown below, and that system looks like a proper nodal source to me. Which of the following statements is true? Well, just to give you a little bit of an idea of why this works the way it does, because I personally have a lot of trouble connecting, the linear independence of the eigenvectors with the proper or improper nodes. Let's think about what is really going on here. If our solution, let's have x of t is equal to c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2 t, and we kind of just ignore, let's ignore these e to the lambda t's for now. Let's just, and this is obviously not x of t anymore. Let's call this y of t, but this still says something about the characteristics of our eigenvalues and eigenvectors here. What does it say about these two if we can get a vector out of it that points in every single direction? Because if you look here, it's pretty clear to see this system is producing vectors that point literally anywhere, and they're always radial out from the origin. Well, that means that you can get to any point in 2D space using both of these vectors, and that means that they are linearly independent. If they weren't, they would not span all of R2, and we wouldn't be able to get this kind of behavior that we see with angles, well, vectors that can produce any angle that we want out of the whole 360 degrees. And I think likewise, if you went and actually analyzed an improper nodal or an improper node in general, you'd see that there are some I think I'm actually kind of just making things up at this point, but the converse should hold, so that for improper nodes, you shouldn't be able to span all of R2 with your eigenvectors, whatever. But for our purposes here, I hope that makes a little bit of sense. So we have real positive equal eigenvectors that are, so the eigenvalues are real positive and equal, and the eigenvectors are linearly independent. And of course, they're positive because we're flowing away from the origin as time goes on, so that our e to the lambda t's just keep increasing. So that pushes us further and further away from the origin. And yeah, they're equal, so we get a proper node. Okay, perfect. Fine. Question 5. Let's find x2 evaluated at 1 if all of this is true. We're told that we have eigenvalues of 1, 1, and 3. And this is probably the only multiple eigenvalue question we're going to have to deal with for this whole exam, which is pretty nice. So let's plug in lambda is equal to 3 to a minus lambda I. We'll get negative 2, 0, 0, 3, negative 2, 0, 1, 0, 0. We can simplify this thing down to 1, 0, 0, 0, 1, 0, 0, 0, 0. And since x3 is the free variable here, we get an eigenvector of 0, 0, 1. For lambda is equal to 1, a minus lambda I gives us 0, 0, 0, 3, 0, 0, 1, 0, 2, which we can simplify down to 1, 0, 2, 1, 0, 2, oh, no, sorry, 1, 0, 0, 0, 0, 1, 0, 0, 0. Sorry about that. And really, I should write it like this: 0, 0, 0, 0, 0, 2. Sorry, 0, 0, 1. Ah, God, sorry about that. Okay, so what this means is that because x2 is our free variable here, our eigenvector is 0, 1, 0. But the problem is we only have one associated eigenvector, and this eigenvalue has an algebraic multiplicity of 2. So we have a defect of 1 that we have to rectify here. And we can figure out our generalized eigenvector. And I'll label these v1, v2. We can find our generalized eigenvector by setting up a nice little augmented matrix with a minus lambda I on the left side and our v2 on the right side, 0, 1, 0. And all we're aiming to do is to get this left side into the same form that this set of 9 values was in when we were able to solve for v2. And whatever is on the right here will be our generalized eigenvector. It's weird how this works. I'm not exactly even sure why, but it does. So let's start solving. We get 1, 1/3. We'll subtract that 1/3, negative 1/3, and divide by 2, 1/6. Now, if we want to, put this into exactly the form that we had over there, we'll have to switch some things around. And there we go. These 9 are the same as these 9. So these 3 will be our generalized eigenvector. We'll call that v3. And that will be 1/3, 0, negative 1/6. Perfect. So what will the form of our overall solution look like? Well, that will be x of t is equal to c1 v1 e to the lambda 1 t plus c2 v2 e to the lambda 2t plus c3 and then v2t plus v3 e to the lambda 2t. Let's replace all of these. X of t is equal to c1 v1 e to the lambda 1t plus c2 v2 e to the lambda 2t plus c3 v2 times t, so that's 0, 1, 0, t, plus v3, so 1/3, 0, negative 1, negative 1, 6, e to the lambda 2t. Great. We can solve for these C1, C2s, and C3s given our initial condition here. X at 0 is equal to 1, 1, 1, because x at 0 will give us C1 times 0, 0, 1 plus C2 times 0, 1, 0 plus C3 times 1/3, 0, negative 1, 6, because this whole term in here will be multiplied by t, which is equal to 0. And we know that, sorry, this isn't x at t, this is x at 0, and we know that it's equal to 1, 1, 1. Now we can just make this into an augmented matrix. We're taking a linear combination of 0, 0, 1, 0, 1, 0, and 1/3, 0, negative 1, 6, and setting that equal to 1, 1, 1. Solving, we can multiply row 1 by 3 and add 1/6 times row 1 to row 3. That gives us 0 here, and plus 1/2 is 3/2. So going back up to our x of t, we see that C1 is equal to 3/2, C2 is equal to 1, and C3 is equal to 3. And I'm going to get rid of this so we have some space to actually answer. What did I do? There's a bracket. Okay, because we are finding x2 at 1 if x2 is the second row of this vector valued function here. So x2 at 1 will be 3/2 times 0 e to the 3, so that's 0. And then we have 1 times 1 e to the 1, so that's e. And then we have a 0 in row 2 right there, and a t there, so that gives us plus 3 e to the 1. That's just 4e, and we're done. Question 6, how many critical points does the following system have? Let's rewrite these a little bit, but after recognizing that if x is 0 and y is 0, this will be a critical point because it will be a solution to dx dt equals 0 and dy dt equals 0. So 0, 0, 0 is a critical point. And you can just find that shortcut or cement that shortcut in your mind by remembering if you don't see any constants, if you don't see any like +2 or -3 over here, 0, 0 is guaranteed to be a critical point. Now let's rewrite these a little bit and set dx and dy dt equal to 0. So 0 is equal to x times 14 minus 1/2 x minus y, and 0 is equal to y times 16 minus 1/2 y minus x. What if y is equal to 0? Well, if y is equal to 0, this whole equation is 0, and this guy is simplified down a little bit. 0 would be equal to x times 14 minus 1/2 x minus 0 for that y. And so this has solutions for x is equal to 7 and x is equal to 0. Well, x and y both equal to 0. Well, we already have that. That's our 0, 0 point. But 7, 0 is a new critical point for us. Now we can do the same thing for x. What if x is equal to 0? Well, this whole equation will be 0, and we'll be able to solve this guy a little bit more easily. So if x is equal to 0, we have y times 16 minus 1/2 y, and this has solutions. Oh wait, I didn't do that right, did I? Yeah, sorry about that. It's not 7, 0. Let's rewind a second. This equation right here, when we had x times 14 minus 1/2 x is equal to 0, that doesn't have a solution for 7, 0. That's 28, 0. 28, 0. Yeah, sorry about that. Okay, and likewise down here, we're going to get 0, 32. as a set of points that solves both of these equations. And then finally, what if x and y are both not equal to 0? Well, then we can divide both sides by x and divide both sides by y, and we'll just get 0 equals all of this stuff. Let's move a y over here. So y is equal to 14 minus 1/2 x, and we can replace that in here. So 16 minus 1/2 times 14 is minus 7, plus 1/4 x minus x. So that's minus 3/4 x is equal to 0. 16 minus 7 is 9. We will set these equal to each other. Multiply by 4, 36, divide by 3 is 12. So we have 12, comma, then if we plug that x into this 14 minus 1/2 x right here, we get 14 minus 6, which is 8. So those are our 4 critical points. And yeah, there's nothing else. That is all that we get. And so D is our answer. Question 7, the following is a predator-prey system. It has some critical points. 2 of those critical points are saddle points. One is a spiral source and one is an asymptotically stable node. If the initial condition is 2, 2, which of the following is true? So pretty much we're just going to linearize the system, identify the behavior at each one of these points, and it's nice of them to give us kind of a checklist to make sure we're on the right track, telling us the behavior of all the nodes in general, and then we're going to graph it out and figure out what's happening overall. So if this expression, we'll call that f, and this guy we call g, then the Jacobian of x and y, which is our linearization of this almost linear predator-prey system, will be fx, fy, gx, gy. And actually solving for those, we'll get 2x minus 2 minus y minus x, y, 2y minus 4 plus x. And since we know what our critical points are, we can just go in and plug those in directly. So the Jacobian of 0, 0 will be negative 2, negative 4, negative 2, negative 4, 0, 0. And what is that? Well, if our eigenvalues are real, unequal, and negative, that will be an improper nodal sink. So that's our asymptotically stable node here. So I'll just say that this guy is our 0, 0 point. And just to save some space, I'm going to get rid of that. What about 0, 4? The Jacobian at 0, 4. Well, plugging in 0 for x and 4 for y, we will get minus 6, 0, 4, and 8 minus 4 will just be 4. So that is a saddle point. Because it's lower triangular, we can just take the values on the main diagonal to be our eigenvalues. And we have 2 real, unequal, and opposite signed eigenvalues. So that is a saddle point. So 0, 0, 4 is a saddle point. Now what about our next point? 2, 0. Guessing it's going to be another saddle point. These systems generally tend to be symmetric like that, but let's figure it out. We get 2, negative 2, 0, and negative 2. So yet again, upper triangular. So we have an eigenvalue of 2 and negative 2. So that's another saddle point, 2, 0. Finally, we're plugging in 3, 1. Actually, we don't even need to because we know that this will be our final point, the spiral source, which is going to have to be at 3, 1. But let's make sure that we've linearized our system correctly such that we should get a spiral source if we plug everything in here. So we get 6 minus 2 minus 1. That'll be 3. Minus 3, 1. 2 minus 4 is negative 2 plus 3 is 1. Okay, solving this system for our eigenvalues, 3 minus lambda times 1 minus lambda plus 3 is equal to 0. Lambda squared minus 4 lambda plus 6 is equal to 0. 2 plus or minus the square root of 16 minus 4ac. That will be minus 24, so minus 8 in here over, sorry, the square root of minus 8 over 2. That will give us a complex conjugate pair with a positive real component, which means we'll get a spiral source. Exactly. So if we were to go and graph this thing out, if we know that our origin is an asymptotically stable node, so it's going to be and how about this? I'll just put a plus next to it so we know that it's pulling things in, attracting things from the general vicinity around it. Now what about 0, 4, and 2, 0? Those are saddle points, and we know that saddle points are repulsive in that they are asymptotically unstable. So they both get minus signs. And then finally, we have a spiral source at 3, 1. And a spiral source, the source point, just like our asymptotically unstable node here, will also be, this is, okay, sorry, I got a little turned around. This is an asymptotically stable node. This will be unstable, so we'll also get a negative sign because it's pushing away points in the general vicinity. Okay, if our initial condition is 2, 2, that will land us right in the middle here. We're getting repelled by this point, repelled by that point, repelled by this point, attracted by that point. Where do you think it's going to go? It's going to go right to the origin. So both populations go to 0. And it's that's it. Yep. And that's it. This is a 6.4 question. It's pretty easy, but we're not going to do it. Hopefully this was helpful, and I wish you luck on your midterm 1 or whichever exam you are reviewing to study for.